Thanks for coming for the second lecture again. Maybe before we head forward, let me just recall also for myself what we did yesterday. So we had to look at the diagrammatic language, leading into the definition of a Markov category with the basic properties of copying and discarding. And then we looked at several examples of concrete Markov categories, so discrete probability, so negative probabilities, measure theoretic probability, and then also this example of the C-star algebras, commutative C-star algebras. And yeah, that's where we ended. I think I'll just get rid of this. And maybe before we go on, are there any questions from yesterday? Something was unclear. Yeah, if not, then let's see where we head next. So we talked, yeah, I need the hockey stick. We talked that, I guess, with the focus on the diagrammatic language, I was trying to argue that one of the advantages is that we can have like a visual representation of probabilistic processes, conditional independence, and maybe even give like arguments about probabilistic processes in terms of the diagrams. I mean, this we haven't seen so much, but that also comes later. And indeed, it kind of really like highlights the conditional independence relations, where in the standard notation for probability theory, this is not always explicit. Like we have to add additional equations, or yeah, it's maybe a little bit in the background. Another point that I made a little bit, but we didn't go into the full details, is that in some sense we can try to generalize the standard probability theory by going to this more abstract categorical perspective. But maybe that's not enough. Like that's kind of nice, but that's not really what drives us in like to do all this work and put so much effort in. So one of the ways in which we use the framework in the projects that we have been undergoing so far is some kind of pipeline like this. So let me try to give you a sense of what we can use the framework for. So we look at some feature, a feature of uncertainty calculus probability theory that we think is relevant. It has an interpretation. It is useful in constructing arguments or somehow reasoning about probability. And for example, that could be the fact that we can take a joint probability and construct the conditional. So this is some kind of feature of probability theory that we like. And then the task is to extract somehow what is the key structural property of this fact about probability theory. So we try to extract this key property and express it in terms of this categorical language of Markov categories, which for the case of the conditional probabilities would be the Bayes theorem that we saw, the fact that maybe we can factorize a joint state into the product of the marginal and the conditional, but in a diagrammatic way now. Once we have this axiom, so this would be like an axiom for the diagrammatic reasoning, then we can use diagrammatic arguments so on the right-hand side, this is the categorical level, to prove a theorem in the categorical language. So this could be, for example, De Fineti's theorem in the language of Markov categories. And once we have such a categorical theorem, then we can look at like in which Markov categories are the assumptions of this theorem satisfied, and instantiate it to obtain now a concrete theorem in some particular model of probability theory. So for De Fineti's theorem, that could be like the standard formulation of De Fineti's theorem in measure theoretic probability in Borel-Stokes, but we could also instantiate it in some other Markov categories. So this Markov category here is not one that I mentioned in the yesterday's lecture, because it's a bit complicated to define, and it's also not exactly clear what is the interpretation, partly because it's so technical, it's a bit hard to extract what it means. But it is an example of a Markov category where the assumptions of the synthetic De Fineti theorem are satisfied, and so we directly obtain a version of De Fineti theorem in that situation. And so this kind of pipeline is what a lot of our papers have been about, where we try to formulate some axioms that capture a feature of probability theory, and then use these axioms to prove categorical theorems about Markov categories, and then instantiate this theorem and hopefully recover at least the known results about classical probability theory, but hopefully also some new results that maybe people have not studied so far, or something. Yeah, we'll learn something new. Does that kind of make sense as an approach? So having this in mind, one of the key features are these axioms. So these axioms for Markov categories, which are additional properties we can require a Markov category to have. And so in today's lecture, I would like to discuss those. Like on top of the basic structure of Markov category, what additional properties can we require that then help us do these abstract arguments? Because just with the bare bones Markov category, I mean, it's nice, we can draw the diagrams, but we cannot hope to prove somehow deep theorems about probability theory. Okay, so let's try to do that and think about what additional concepts and axioms we can think about in the language of Markov categories. The first one that I want to talk about is the idea of conditionals. This has already appeared in yesterday's lecture when we were talking about Bayes' theorem, for example. And so this is the diagrammatic Bayes' theorem that we were talking about. But we can also, so here we have some Bayes' theorem for joint probability distributions or joint states. But we can also consider another kind of version for morphisms where we include another input. So now we have a morphism with one input and two outputs. And we say that if for any such morphism f, we can write it in the form on the right where we have the marginal in here, the conditional in here, and then the input is fed in both to the marginal and the conditional. So to say, when we have a parametrized joint probability distribution, then the conditional is also going to depend on the parameter. So that's what the diagram on the right says. And so whenever this new morphism f given a exists for any f, we would say that the Markov category then has conditionals. And this is an additional property that need not be satisfied in a general Markov category. Is that somehow clear, the idea? Now we can ask, in which Markov categories do we have conditionals? So from the examples that we have seen, we have the Finstoch and Borel-Stokes. So these have conditionals. The possibilistic case also. And then two examples which I have not mentioned. So this is a Markov category for Gaussian probability distributions. There we can also form conditionals which are going to be Gaussians. And this quasi-measurable case, there we also have conditionals. On the other hand, if we look at the topological case, there we do not have conditionals basically because conditioning is in general not going to be a continuous operation. And here we require continuity of the kernels. In the case of the negative properties, we also don't have conditionals. That is an exercise on the second sheet to show that. And in the algebraic case, there are also no conditionals in general. If you specialize to some particular, it's basically because this is going to correspond to the topological case. Yeah. And so here we already see that from the landscape of possible Markov categories, we have some kind of splitting between some Markov categories that have nice properties, like conditionals, and some other Markov categories that maybe do not have these properties that are like what we expect from classical probability theory. Okay, what about what do we have next? Like from conditionals, this is not a new axiom. This is just a different way to think about conditionals, or like what we get from conditionals is that if we have a joint state, then we can form conditional of Q given A on the right-hand side, or a conditional of Q given B on the left-hand side. So this is both using the axiom of the fact that conditionals exist, and then we have this equation between the marginal on B and the conditional of A given B, marginal of A and conditional of B given A. And so in this way we can relate somehow the kind of reverse conditionals, P of A given B and P of B given A, which gives us a notion of Bayesian inversion. So this is now can be seen as a special case of conditionals. Like whenever we have conditionals, then we also have this notion of Bayesian inverse. So for any morphism F and some prior state R, the Bayesian inverse is any morphism here F dagger with a subscript R because it depends on R that satisfies this equation between the very left-hand side and the very right-hand side. So in this way, this gives us a diagrammatic way to talk about Bayesian inversion, which can be handy sometimes. And maybe to have like some concrete example of what this looks like, because this also shows up later in some proofs. If we are in the Finstock, so discrete probability, and B is just a 3-element set, and A is a 2-element set, and this prior state gives probability 1/2 to 0 in B and 1/4 to the other 2 elements, then we can consider a coarse graining map F that just identifies the first 2 elements, so 0 and 1. And then the Bayesian inverse would be a kind of partial inverse of this map that's, however, stochastic, where it preserves the part that is not identified, and for this element here, we obtain a kind of measure on the input that corresponds to somehow the ratio between the probabilities that we originally had in R. And so what we get in this case is that if we look at the Bayesian inverse followed up by F, then this is just identity on A. So if we look at the Bayesian inverse, F dagger, and then coarse grain by F, then this is just identity on 0, 1. And in fact, this property that we see here can be proven diagrammatically in any Markov category. So this is just an example of once we have these axioms, then features of, for example, Bayesian inverses that we have in probability theory, then just follow from the axioms of Markov categories. And in this way, they are kind of captured by the abstract language. Yeah, hello.
In the case where kind of the marginal on A doesn't have full support, so the conditional B given A is only defined on the support.
Yeah.
Okay. Do you have to modify the adiabatic equation, or is that special case included?
Is included. In this case, it's included because anything that is given probability 0 by R is going, like the equation does not place any constraint on that.
Well, it would be given probability 0 by F, not by R, right? Because you're computing a conditional B given A.
Yeah, indeed. So here it's about probability 0 under F composed R, indeed. And so whenever that is the case, whenever there is an element of A that is given 0 probability, then the equation is trivially satisfied always. Because somehow multiplying 0 probability by anything else on B is going to be 0, and so the equation is satisfied whatever the inverse is. And so that means that in some sense there is a non-uniqueness in the conditional, or in the Bayesian inverse in this case. So the property of conditionals is that there is such a conditional, but we don't say whether it's unique. So there could be many conditionals, and indeed, in general, they are not unique. So on the support, they are specified by the equation, but outside of the support, they are arbitrary.
So this definition basically says you can have anything outside the support of the distribution on A for your Bayesian inverse.
Yes.
Which is not the conventional way of doing it. You conventionally just say this is not defined. You're sort of allowing it to define any way you like. And
yes. Yeah, I think there are different approaches, and yeah, in the end, the way in which we deal with this somehow problem is also this equation you see here. It will not be satisfied in general if we have somehow less than full support. It will be satisfied up to almost sure equality, so with property 1. So,
is that in the case of the measure theory? Like in
yes,
the discrete case,
that's also the case in the measure.
At all, like it's only satisfied on the support, which could be different from full support.
So it's going to be satisfied on the support, which means there's probability 1 that it's satisfied, because anything outside support has probability 0.
Okay.
And so this holds also in measure theory, and this is kind of, it shows up a lot in the theory that a lot of the statements are going to be up to probability 0, or in the categorical language, almost surely. Yeah. But there is an alternative, one could develop an alternative definitions where you rather say, like, I have morphisms that need not be defined for every input, so they're kind of partial morphisms. And then you could rather change the definition and say, it has to be somehow unique. And if you require uniqueness, then that forces it to be a partial morphism. And then, like, I think there are ways to kind of connect the two approaches, but most of the time we kind of take this approach. But yeah.
Is it fair to think of your approach as any 0 probability, assume that in fact some very small probability, so that you have full support, do everything, and then take the limit? That would seem to give the same sort of result.
I think I didn't follow. Sorry.
Well, you sort of let's say I have a case where that my support on A is not full support.
Yeah. Mm-hmm.
There's some zeros. So one thing I can do is say, well, let me move to a nearby case where all those zeros are actually epsilon, some very small probability. Now I do have full support. Bayesian inverses make sense.
No, we cannot do this in general because, I mean, in discrete probability you could do that, but for many of the other Markov categories, you don't even have any full support state. Like there will be, so for example, for continuous measurable spaces, there is no probability measure with full support. And so this will not work.
Why do you say there's no probability measure with full support?
It depends how you define support, of course, but we have, for example, a categorical notion of support, which is kind of the one that you would need. And that one, for example, for the Borel-Stokes, so for example, the real line, there is no state with full support.
Okay, so that maybe I need to see your definition of support, because I would have thought like a Gaussian has infinite tails, so I would say, yeah, that has full support. It's not compact, so it has full support, but you have some other notion of support in mind.
So the Gaussian will still, yes, it's a notion it's about, I think it's a kind of topological notion of support. No, what do you have in mind? I think it's the topological notion, and then there is a measure theoretic notion. And so in the measure theoretic notion is about like the set of all points that are given non-zero probability. And so the Gaussian still gives zero probability for every point.
Oh.
And so really the almost surely notion is really the right version in some sense, like because we are interested in like what set does the Gaussian give property 1 to? That's kind of the notion of support, and that's why working with almost sure equalities kind of ensures that we somehow take care of the support.
Okay, why don't you continue?
Yeah, I think actually we get to almost surely very soon. I will skip this to move on. So one thing that we mentioned also yesterday was conditional independence. And so given a tripartite state like this, we can express the fact that A and B are independent given another output C by an equation equation that Q decomposes in this way, where here's some arbitrary state and two arbitrary morphisms of A given C and B given C respectively. But we also have conditional independence for other kinds of morphisms. So we could have a morphism with an input and two outputs, where the two outputs should be now independent given the input, and then it looks something like this. Or we could have, there's actually several other versions. I just give another one extra, where we have two inputs and one output, and we want to require that the output and one of the inputs are independent given that the last input, and then it would be some kind of decomposition like this. And in the discrete probability, they correspond to somehow different ways of expressing the fact of conditional independence, which in the case of just discrete probability theory are actually equivalent. But in a general Markov category, these are just different notions for different types of morphisms. However, what you may have, if you had a look at the exercise sheet, then you would have seen the semi-Graphite axioms. These are implications between different conditional independence relations. And one can show 3 out of the 4 just by simple diagram manipulation of using the Markov category properties. If we additionally have this axiom of conditionals that we just mentioned, then we also get the last semi-Graphite axiom, and also we get a kind of equivalence of these definitions of conditional independence again, almost surely. And so having conditionals kind of gives us a way to explain why these somehow seemingly different notions of conditional independence in discrete probability theory are equivalent to each other. Okay, now we go on to like one of the very basic notions. Yeah,
Sorry, I might have just missed something.
Yeah.
Did you say weak union doesn't follow? It does.
Yes, it does not. So out of the 4 axioms, 3 follow directly from the properties, and to prove weak union, you also need conditionals.
Oh, sorry. Yes.
Yeah. Mm-hmm.
And what about intersection? I think
The
the
contraction.
axiom that holds, for example, for probability distributions only for ones with full support.
I don't remember. I don't know. Yeah, maybe we can have a look at it later, but I don't remember it now. Okay, so now having talked about conditionals, let's look at one of the really basic notions in Markov categories, which is the idea of determinism. So we can consider morphisms that commute with the copying. So we already have seen that we require every morphism to commute with the deletion, this the normalization condition, but we don't require every morphism to commute with copying, because that expresses a certain notion of determinism, which, if we want to describe uncertainty, we will not want to have for all morphisms. But the class of morphisms that do satisfy this are very important. We call them deterministic, and they express, indeed, in the examples that we have, they express an absence of uncertainty, absence of noise in a way. If we look at the Finstock case, the discrete probability, then they correspond to functions. In the measure theoretic case, they are measurable maps or continuous maps in the topological case. For the Gaussian example, then they are going to be just affine maps on the vector space without adding extra noise. And in the algebraic case, they are the algebra homomorphism, so they preserve the products. And so in each case, they somehow recover what we would expect from deterministic Markov kernel in a way. Rob?
When you say affine map to the Gaussian case, that doesn't necessarily preserve Gaussianity. So do you mean like symplectic affine maps where you'll preserve Gaussianity? Or?
So here we don't have any symplectic structure. It's just vector space. Yeah, actually, I think I somehow forgot. Like at some point in these notes, I had the Gaussian example explained in more detail, but I didn't now. So there you really have just vector spaces, and the Gaussians are not on the phase space, but just on the vector space.
I see. So the fact that it's affine is sufficient to preserve.
Yeah, then it preserves Gaussianity actually. Yeah. Okay, so this notion shows up over and over again later on. So it's very central to the whole theory. What else do we have? Okay, almost surely. This is what we already talked a little bit about, and it's the idea that sometimes you have morphisms that are not exactly equal, but they are equal with probability 1. And in order to say with probability 1, we have to say with respect to what measure. So we have some prior state P, and we say that F and G are P almost surely equal if this equation is satisfied. And in the case of the discrete probability, this expresses the fact that the two stochastic matrices are the same for any input in the support of the distribution P. So this kind of connects back to the support discussion that we had, at least in the discrete probability case. When we look at the this is what I mentioned before, is that you can also express it as the fact that the probability that the two stochastic matrices are equal, or their outputs are equal, is 1. And very similarly, in the case of the measure theoretic probability, this equation expresses the following fact, that for any event on B, so T is an event on B, and any measurable set on A, we have this integral equation, which again just expresses the fact that the probability that the two Markov kernels are equal is 1. That's equality almost surely. And this is once again a very ubiquitous notion that shows up over and over again.
Why it's called almost surely?
I guess because it's with probability 1, so it's not sure that they are equal, but it's almost sure.
Okay.
So, the probability that they are not equal is vanishingly small.
So the reason that it is defined this way instead of just having one probability distribution without this copying, like
Yes. So you mean like just deleting A?
yeah, just deleting A, for example.
Yeah. So in that case, that would be equality in distribution, and so that would be saying that if I look at the distribution of B according to the Markov kernel and the prior, then those distributions are the same. But these distributions can be, let me see if I can see. They can coincide even if the Markov kernels themselves are very different. Like for example, if I look at stochastic matrix, the identity, so let's say this is F, and another stochastic matrix which is like swaps, well then if the prior P is uniform, then applying either of these to the uniform distributions stays uniform, and so they would satisfy the equation that you were asking. So they are these two are equal in distribution with respect to P, but they're not almost surely equal.
And how the copy changes that?
So the copy changes that we have this output A, and so I think it's easier to see in the discrete probability case where that gives you this quantifier for all A, because it's for any output A,
Okay.
right?
And what if we don't even have an input distribution? You just compare the morphisms from A to B.
Yeah, then it would be just equality of the morphisms.
Of course, and then
So there are different notions of the equality, and sometimes equality of morphisms is too strong. Like, for example, when we consider conditionals that are only defined uniquely, almost surely.
yeah, right.
Can you say it again? What happens when P equals 0? You said then the equations are truly.
Right. So, in some sense, this equality requires F and G to be equal. So, in this sense, equal whenever the probability of A is non-zero in the discrete case. But when the probability of A is 0, then we don't require them to be equal, and they could be actually arbitrarily different.
Okay.
Yeah, there is no constraint for those inputs.
But in that case, the equation still holds. Is the point.
Yeah, indeed, the equation holds, and therefore it places no constraint on what F and G should be in that case. Yeah.
Okay.
That's right. Okay, so it's almost surely. Okay, now we go into more of somehow detailed axioms that can kind of, in some sense, express whether our Markov category that we are working with is close to what we would expect from probability theory or not. And one such axiom, which has been quite useful in a lot of the proofs that we have constructed, is the positivity axiom. And this axiom says the following, is that for any morphism with one input and two outputs, such that one of the marginals is deterministic. So we have, I mean, maybe one easy way to think of it is for a trivial input where we just have a joint state where one of the marginals is deterministic. Then under the positivity axiom, it should be the case that the joint splits. So it basically gives you this conditional independence of the two outputs. And so one way that we call, like this property, we also call the deterministic marginal independence, is that if you have a deterministic marginal, then that marginal or that output is going to be independent from everything else. And this is not true for any Markov category. So there are Markov categories where it is false, but it expresses a kind of positivity in some of the examples that we consider. So if we write out somehow this definition in terms of the just probabilistic language, then on the left-hand side, this marginal equation says that if we have zero probability for some P of A, which is just the marginal of the joint, then it should also be the case that the joint probability, which splits in this case because it's independent under this equation, should also be 0. And so this is satisfied because, yeah, we have P of A and P of A here.
Tomasz,
Yeah, sorry.
you said that that second line was an if and only if to the first line.
Yeah, I think that's not true. I think I realized while I was talking about it that it's not true.
It's an implication of the first line. I can't necessarily get back to the first equation.
Yes, yeah, for sure. Yeah. I think what I wanted to say is that I think I didn't write this very well here, but if you have a marginal that the probability of the marginal event is 0 and you have negative probabilities basically, then you can have several non-zero joint probabilities that sum up to 0. And then it's no longer the case that the joint probability has to split as a product. And so basically this implication fails if you have negative probabilities, which is also one of the exercises on the exercise sheet, is to show that if you have negative probabilities, then you do not have this property. But in any of the examples of Markov categories where we have seen that they have conditionals, you can show that conditionals imply positivity, and so there we always have this property. But additionally, also in the topological and algebraic case, we also have positivity. Well, in the algebraic, yeah, it depends whether we consider positive maps or not. But yeah, and so in some sense, I guess in a lot of the examples that we have, positivity is satisfied. But there are also some interesting examples where it's not. But in a way, because conditionals imply positivity, but not vice versa, positivity is a kind of weaker property that even if we don't exactly have conditionals, sometimes positivity is sufficient to get us going.
And this implication also said that if we, like the reverse directions, if we don't have positivity, then we cannot
Exactly.
derive. I see. And then that's the reason why in Finstock we cannot always have conditionals, because we do have the case where PAP is not 0.
Right. So in with the negative probabilities, you will not be able to form conditionals in general. Yeah. Mm-hmm.
So this means that in Finstock, conditionals are not valid, right?
In the Finstock plus minus, so the one with negative probabilities.
Sorry.
Yes. Mm-hmm. Exactly. That's
Nice.
right. Okay. What else? So we have like 15 minutes extra. Now we get. So until now, I was talking about properties that have to do a lot with decompositions of the string diagrams and kind of, yeah, like diagrammatic properties. And these are useful, but they are not sufficient always to express all the concepts that we would like in probability theory. And so now we get into different kinds of axioms, which are rather defined in terms of more machinery of category theory. I will try to explain them somehow without going into all those details, but hopefully we can still understand what's going on and the intuition. Okay, so one of the most important ones is this idea of a distribution object. And the idea is that we would like to be able to talk about not just measures, but also the space of measures itself, and in particular, measures over the space of measures. So kind of nested uncertainty. Like maybe there is some uncertainty we have about the situation, and there is some additional uncertainty about the uncertainty. And so that will be a kind of situation where we have a measure on the space of measures. And this is not the only case where it shows up, but it is a kind of important concept to be able to have this language to talk about such situations. And distribution objects is the concept that allows us to do that in the categorical language. Okay, so what is the distribution object? Consider a state on some system A. Then we would like to say that any state on A can be seen as an element of some other object, right? We want to have an object that expresses basically whose elements are the measures. So on the left-hand side, we have measures or distributions on A, and on the right-hand side, we would like to have the elements of this space, so to say. So now I'm using kind of more like set theoretic language, but that's kind of the intuition that we use to then generalize to the categorical language. And the categorical way would be to say that we have a bijection between states on A and deterministic states on some other object P of A. So P of A is going to be the space of measures over A, so to say. And this bijection kind of expresses the fact that somehow it kind of gives us reason to like use this interpretation.
Much is there a term in category theory for when you do this kind of thing, where the objects in your new category now range over the morphisms of your old category? That's sort of what you're doing. Like you have, the morphisms of the measures on the left, and now you're saying, but now I'm going to introduce a new object, which is a set of possibilities that ranges.
It's still morphisms. They are just particular kinds of morphisms.
No, I know, but the object P of A is kind of morally playing the role that Q played on the left now. It's
Enrichment?
Is it that's called enrichment?
This notion of enrichment, right, where the morphisms are replaced with objects in another category. Is that real?
There are several ways to do what you mentioned, and there are also ways to relate them. So here, I don't know like how much you've heard about this stuff, but here we are using a notion of a monad. So this is going to be kind of assigning to A another object which is kind of like a structured version of A, where it has A with some structure and is the structure of the space of measures over A. But another way to see it, there's like different ways to kind of see it. But I think monad is the kind of like the closest concept in category theory that we are using here. But we would like it to be true also not just for states, but also for morphisms. I mean, in category theory, we really care about the morphisms. And so we would like the same bijection to be true also with some input.
So can I ask you,
Yeah.
the main difference there is that in this new thing that you have, everything's going to be replaced by deterministic stuff? That's what's happening?
Not everything is deterministic. I mean, there will be some deterministic morphisms into PA, and those are precisely the general stochastic morphisms into A. So PA is in some sense much bigger than A.
Okay.
And
The things that were in A get mapped to...
yeah, I mean, I will give example very soon, so maybe it just comes up, but like if A is like 0, 1, just the coin like outcomes, then P of A would be the unit interval, basically. Because this is the space of distributions, like space of possible coin biases, right?
Mm-hmm.
And so then the deterministic points here is a distribution over these.
I see.
But there are also non-deterministic distributions here,
Yeah, of course.
right? And there will be the measure over measures.
I see.
Yeah. Mhm.
Thanks.
I think that comes very soon. Oh no, not yet. So also the distribution objects is a kind of property that we have in a lot of examples, which is nice because they are useful. So in the measure theoretic case and basically any time that we have sufficiently large spaces, but for the finite case, that is not going to be the case. Like we see it here, like P of A, even for a finite A, is going to be infinite. So that is not going to be within the space of finite sets. But for example, for the multivalued functions there, it's possible because the space of multivalued functions is finite, even, because there are only 0, 1 valued.
Can you explain a bit more what does finite, not finite relate to the existence?
Right. So if I have A be the outcomes of a coin, so just 0, 1, then the set of distributions over A is going to be given by the set of possible biases of the coin. But there are infinitely many biases, like is any element in the unit interval. And so P of A on the right, the distribution object, would have to be an infinite set, the unit interval,
Okay.
right?
And why it's a problem?
So it's not necessarily a problem, but in the definition of this category, we said we only consider finite sets. And so it's not going to be inside the category.
So there, what you're saying is not the Markov categories that you can or cannot do it, is whether or not PA can be one of those categories. Is that
You can live in the
Exactly.
sorry?
If there is such an object PA,
It's not in Finstock.
it's not going to be in Finstock, it's going to be in some larger category.
So
yeah.
what I'm saying is that the bottom part of your slide is not referring to which Markov categories you can do with this distribution object. It's just saying what PA can be, right?
No, it's the first. It is, so I'm talking about in which categories it is possible to have such a bijection. For each object A to have a corresponding distribution object PA. Well, in Finstock, there are objects, in particular any non-trivial object, for which the P of A would not, there is no P of A inside the category. And so there are no distribution objects.
P of A, sorry.
I guess like a distribution of it has a particular definition that you haven't really given. yet,
Yes.
and that just doesn't exist within things.
I mean, the definition, there are additional elements that I didn't spell out here, but like the main thing is this bijection, and already this bijection is not, you cannot satisfy it in Finstock, because in order to have the bijection, P of A would have to be in an infinite set.
Okay, can move on. I don't understand, but we can move on.
I think just by definition, PA and A have to be in the same category.
Yes,
Okay, this I didn't, okay.
yes,
That's the point I was missing. Okay.
thank you. Okay, I think what I already said here is that, yeah, if we have some measure over like 3-element set, like this one, then on the left-hand side it's the measure, but on the right-hand side it's just a point within the space of measures, like in this case, the free simplex. And so that's kind of how we think of it. Like we have measures on the one and the space of measures on the other. I will skip this in the intro time. Okay, given a distribution object in this bijection, we can see what are some of the consequences of having such a distribution object. The one consequence is that on the left-hand side, we can consider the identity. So the bijection should be true for any morphism, so in particular, it should be true for the identity. And then on the right-hand side, we get the corresponding deterministic morphism that goes from A to P of A. Can someone guess what this morphism does? I mean, the name kind of is suggestive, maybe. It takes an element of A and it outputs the delta measure on A, right? So for any point in A, this morphism, deterministic morphism, it maps the point to the delta measure, which would be an extremal point in the space of measures of A. And so this gives us a kind of categorical notion of delta measures, basically. One other consequence is that on the right-hand side, we can also consider the identity. So identity is always deterministic, and so we can consider what happens under this bijection when we have a identity on PA on the right. Well, then it should correspond to some morphism on the left that is not necessarily that deterministic, which takes a measure in P of A and outputs basically a distribution over A. And again, the name is somehow suggestive. We think of it as the sampling map, which in Borel-Stock, the way you would write the Markov kernel is that it is the conditional probability of some event given a measure, which just gives you the probability of that event according to that measure. It's just an evaluation map, basically, of the measures. And the reason why we think of it as a sampling is that in the picture where, okay, we have elements of P of A, so an element of P of A in general is some measure, some point in the free simplex in this case for the free outcome A. And the sampling map maps this measure Q to the distribution of outcomes of A with probabilities according to that measure. So it is really kind of like, it's really the identity, but it's identity where the type is P of A to A.
And when you plug in like a non-deterministic state at the bottom, you would get sort of the average.
Yes, you would get kind of the mean of measures. Yeah.
And so I say that any Markov category with distribution objects has these maps.
Yes, they're kind of quite, they are quite useful. Also because they satisfy a lot of nice properties that comes from some of the properties of distribution objects that I did not tell you. So yeah, I think I'll get to that on the next slide. But yeah, in any Markov category with distribution objects, you have delta measures and you have the sampling maps. And yeah, so one of the properties that I did not tell you yet that are also required for distribution objects is what in category theory we would call somehow naturality condition, which is that if we consider a composite morphism on the left, then we should still be able to have the same bijection. So then we have somehow, I don't know if I explained this notation, but the bijection from left to right we often denote by the sharp. So the image of the morphism on the left on the right is just given by the morphism with a sharp. And then we would require that whenever the initial morphism is deterministic, then the sharp of the composite is just applying the deterministic morphism and then the sharp of the second morphism. I will not go into the detail of exactly why this is required, but it is a nice property that is satisfied in a lot of the examples, and it gives, it's somehow very natural from the categorical perspective, and it gives us a lot of kind of machinery to work with. So in particular, one of the consequences is that I think I will not go into details of proving this, also in interest of time, but we can talk about it later if you want, is that if I have any morphism f, then I can decompose it into its sharp version and just sampling. Basically, I consider the kind of deterministic version of f, which is kind of the measure associated to f, and then I just sample from that measure. Or, in other words, or like the reverse, in whenever I have a deterministic morphism G, well, then applying G and then considering the delta measures is actually the way I would obtain the sharp of G. And so, yeah, these properties make a lot of the proofs work when we work with distribution objects, and that's also one of the reasons why we want to require such a kind of consistency of the bijection with respect to composition.
Sorry,
Yeah.
the distribution object refers to what? What is a distribution object?
That's a bit hard to get from this presentation, I think. Often we talk about distribution object as just this P of A. So for any A, I can construct the P of A, the distribution object, whenever we have a Markov category where it is possible. But this P of A is not just any object, it has to satisfy some nice properties. And so in particular, I have these bijections, and the bijections are compatible with composition in this way. But when I talk about distribution object, often I just mean the P of A.
Okay.
Yes, of course.
Unless you. Because I was thinking, like, in probability theory, often what you do is like take convex mixtures of stuff.
Yes.
So, like, one thing that is kind of remarkable about Markov categories, I guess, is that they don't have any convex addition structure at all.
Yeah, not from the beginning. Yeah,
I guess this kind of has a flavor of
it goes in that direction. Yeah.
Yeah.
Yeah, so I mean, there's a lot more I could say about it in some sense, but you can equip or somehow, for any Markov category, you can look at the particular kinds of morphisms. In particular, once you have distribution objects, then like in the examples, P of A suddenly has a linear structure. Like this 0, 1 is just a set, but here we have some convex structure on P of A. And this convex structure is expressed by the universal property of the distribution object. In particular, I will not go into the detail, but like the P of SAM is going to be kind of expressing the convex structure of P of A. And you can then, once you have the distribution object, then you can also consider other kinds of means. So convex mixture is just one way of taking averages. But given a distribution object, then you have like you can consider geometric averages, like other kinds of averages. So it is quite powerful somehow to just have this, and that's why it's kind of nice that a lot of Markov categories do have distribution objects, because then we get going with a lot of somehow just convex mixing and stuff like that. And a lot of the statements that we want to prove are in terms of the distribution object in the end. So. Okay, so now we have to make a decision. I have been talking for almost an hour, and you can tell me, like, I can go through another axiom, which is again like different, or if you want, I mean, we can kind of end it here and spend the rest of time with whoever wants looking at the exercises. Do you have a preference? Like, who would like to go further with the axioms? You can raise your hand. And who would like to do exercises? Okay, so there is no clear. I have to make a decision basically.
We ask more questions.
Yeah, we can also just do more questions, and
I don't know, but
I just don't know. Like for me, I can go on, but I don't know like how much capacity more you have to like go through another axiom.
So. Okay, so then
let's just do questions.
The question would be like, how would you define more formally the distribution object? Is that too hard to do?
No, it's not so hard. You can do it. Of course, in category theory, there's various like levels of abstraction. So you can go very abstract, and it's probably going to be very like simple and very non-understandable. Let me see. I will try to not use too much jargon. Let's see. So I will use some notation. So in category theory, we often write the set of all morphisms between two objects. So this is the Markov category C and two objects. So this would be basically the set of morphisms F, which have input A and output B, right? This is also called the Hom set, and so we can use the notation to kind of package the definition a little bit. So one way to say that we have a distribution object is that we have indeed this bijection. So we have C of. Okay, I will change the notation to kind of match that. Sorry. I think we had CA. here. And so we have a bijection between the set of morphisms from C to A and morphisms from C to P of A. But additionally, these ones should be deterministic, right? And in fact, I did not show this, but the deterministic morphism, they form a subcategory and actually also a Markov category.
Okay.
And so this bijection, okay, so this is the bijection that I told you. And additionally, this should be somehow natural both in C and in A. And what this means is a little bit hidden, because in C, this means with respect to deterministic morphism. So here we require G to be deterministic. And then additionally, this is what I did not tell you yet, is that it also should be natural with respect to A, is that if I compose on the top, is also preserved, but there is for any morphism.
Okay.
And the fact that, yeah, like somehow, this is like intuitive because it highlights the bijection, but it's a bit ambiguous, I think, this definition. It's not always so, you have to really remind yourself what it means.
And P of A needs to be an object in the same category, of course, right?
Yes, exactly.
P.
Because this is a subcategory of the original category, so it, yeah,
I see.
yeah.
Should PA just be a function, or is it like an endofunctor or something?
It is an endofunctor, and in fact, it's going to be a monad. So, like, an equivalent definition would be that, like, I have some injection. So when I have a subcategory, so this is going to be a subset of morphisms of the bigger Markov category. So I can consider just the kind of inclusion of the deterministic morphisms in the bigger Markov category. And then the definition says that P should be, I don't know if you're familiar with this notation or terminology, but P should be the right adjoint of I. And this bijection, natural in C of A, is expressing the adjoint functors. Yeah.
Oh, well, that's the same condition.
It's the same condition.
So if it's an endofunctor, there should also be things as PF, right?
Yes, exactly.
So what are those intuitively?
That's a good question. Where do I have space? Maybe, yeah, so for any state, so whenever I have mu, no, not mu, we usually use P on A, then this corresponds to some P sharp, so deterministic state on PA. And actually this is also equal to, okay, now I have a lot of P, so sorry, I will change this. Q sharp, and so this is going to be the P of Q for a state. But now if I have an input, then these are not the same actually, because like the types are different, right? Like Q, so if I have a morphism F that goes from C to A, then this corresponds to, under the bijection, corresponds to some F sharp. And this F sharp has the same input C and output P of A. But then I also have a morphism P of F that goes from PC to P of A. So that's what the functor does. And it's not obvious how to kind of extract it. But you asked about the interpretation. Basically, it gives you kind of push forward measure. So for any measure on C, it gives you the push forward of the measure on A under this Markov kernel. But I mean, you have to do it kind of stochastic push forward. Like usually you have push forwards under measurable maps. So how could we do it? I think it's easier to do it in the...
See it as F sharp composed with the sampling map?
No, it's not the same. So F sharp. How do I do this? F sharp actually. So F sharp is equal to PF composed with delta. But if I pre-compose with sampling, well, sampling followed by delta is not the identity. You can try to think why. And the other direction is true. So if I first consider delta distribution from A to PA, and then I sample to A, then this is just the identity. But in the other direction, it's not true. Because I like...
No, you don't. No.
Like you take...
You don't end up with a deterministic state. Yeah,
Like,
Yeah, you will end up you will not end up with the measure. You will end up with the...
like you pass, you're going from PA to PA, but you're passing through A,
Yeah.
which should be smaller.
Yeah, I mean, it cannot be the identity, but yeah, what exactly it does, I mean, is
you start
maybe
with a distribution, and you sample, and you do delta, and what you end up with is like a distribution
over deltas, exactly, yeah. And not the original distribution, but the distribution over delta functions, yeah. Yeah, so I think you can see it like this, like if you start from the unit interval, like let's describe the unit interval like this is the 0 and this is 1, and like a measure Q is somewhere here, then the composite of sampling and then, so okay, sampling, then, and then delta gives us somehow distribution over Q, which has a Q of 1 is equal to, like the weight of 1 according to Q, and but before it was like a delta on Q here, and now it's like a mix, like a distribution over the deltas, the extremal points, and so it's not the identity. But you were asking about the interpretation of this. Sorry, I think I got distracted a bit. But maybe we can use this example to think about it. So let's say that we consider F something stochastic, so not deterministic. So F is here. Let's consider like a 2x2 stochastic matrix. It sends the first element to the uniform and maybe just preserves the second element, something like that. So what does PF do? PF it has to be deterministic, and so it will take a measure, so some Q inside P of C. So P of C is just unit interval. So we can also think of it as something, this is just the 0, 1 interval. And it should give us another measure on 0, 1, so another element of the interval. So it takes 0 to the uniform. So for example, it maps 0 to 1/2. So that's the uniform. It maps 1 to 1. So it preserves 1. And it kind of interpolates between the in-between. That's the kind of the push forward. So basically, it takes a kind of mixture of these into the mixture of these. So basically, it takes Q to, what would it be?
A half plus a half Q.
Half plus a half Q.
And on the other hand, sampling followed by F sharp would do
I think it would give you a distribution over these two. So just like the sampling followed by data gives you a distribution of the extremal points, sampling followed by F sharp would give you not the interpolation between these 2 points, but the distribution over those 2 points. So they are somehow, of course, if you sample afterwards, they are the same, but as morphisms, they are different. It can be a bit subtle, as you see, like it's not so easy to do like on the spot. But these distinctions become important in the theory, that you can actually use them to express different kinds of statements. Like sometimes, like putting sharps on some morphisms makes the statement stronger, which is then what you need. Like, and I think the fact that the distinctions can be quite nuanced in like standard probability theory is somehow a feature of the language that we have. Is that kind of maybe ambiguities that are easy to overlook in standard probability notation are very clear in this notation. Like you really see somehow the difference between F and F sharp is like even the types are different. While in standard probability notation is not so clear like which one are you actually using.
Because of the overloading of notation.
Yes, exactly. So I see this as a kind of feature of the categorical notation.
And if you guys want to do exercises or move on, go ahead.
No, like,
Just to test.
Yes, ask.
No, that I just did. What I mean is that you made a vote to decide what to do,
yeah.
and I just like disrupted everything. So if you want,
No, I also have another question slash comment still,
okay.
Yeah, that's good.
which I wanted to make whilst Rob was still here, actually. So, because this kind of also reminded me a little bit about like this Omelette paper.
Oh, which paper?
Rob has this.
This in time, yeah.
Because they also these morphisms in your causal theory, which in that case I guess are functions in the classical case. And the other wires which go horizontally,
Yeah.
which are like morphisms or like objects in differential theory, and they kind of specify sometimes distributions over morphisms. Yeah, that's all I had to say. I guess it just reminded me of that.
Yeah, I think
This, yeah.
I don't know like the precise details because I've never worked it out, but I think one can kind of supplement or like generalize the Markov category to have like additional wires like going sideways. Usually, yeah, in category theory, there's sometimes the thing that like you have many options how to generalize stuff, and it's not always so clear like which one is the right one. But my hunch, and like I recently was reading a paper about graded Markov categories. So there are Markov categories like this, but additionally they have some grading. So grading is just like another, like as if you were adding another wire from a different category. It's quite related to its particular kind of enrichment, or like enriched Markov category. And there, I think you have this diagrammatic calculus where you have these somehow two-sided wires, like sideways and horizontal, or horizontal vertical. So that would be one option of maybe going in that direction.
I guess that would be, or it seems to me, that might become sort of more conceptually clear once things start getting complicated. It might be like where to have like both normal objects and distribution objects be the wires that look the same, or would you argue that sort of sometimes you need them, you need to be able to treat them on an equal footing? They seem like conceptually very different types of objects.
Yes, I think sometimes it's a feature, sometimes it's a bug. I think it depends on what you want to do. It's a little bit like, I think when Tobias was developing this in the first place, one of the somehow criticisms or kind of like skepticisms that Rob had about the language was that it kind of conflates influence and inference. Because in the string diagrams of Markov categories, there is no distinction between what is a causal influence or what is just inference. And I think this goes in the direction of what you are kind of mentioning or highlighting, and that's also the reason why they have the unscrambling the omelette paper, because they want to disentangle the influence and inference. And yeah, it is fair to say that in Markov category, these are not distinguished. And similarly, you have A and P of A and PP of A and PPP of A or whatever, like they're all part of the same category, but they may have different interpretations. From the mathematical point of view, often it's nice when they're part of the same category because it simplifies things. But just because it simplifies things doesn't mean it's always the right thing to do. Like maybe sometimes you should not simplify it.
Do things like PPA or PPPA ever show up in like useful theorems?
I mean, even in the definition you have PPPA. I mean, you don't. It's not clear here, but if you think of
It's for all objects,
If
right?
you want to.
And P of A, is it because it's for all objects and P of A is an object, then PPA?
if you think of P as a monad, then you need like the multiplication, like the, what is it called? Yeah, this multiplication law of the monad, and there you have PPPA, for example. But in like concrete results, I think, no, not really. I mean, of course, you can prove like categorical results about somehow like arbitrary amount of P's, and then it's about like, I guess you could. I mean, there are also like people in philosophy of like science who think about like just iterating uncertainty, and like you could ask, like does that like converge, or like is there something that like new emerges when you consider like more and more nested uncertainty? But I think in traditional probability theory that doesn't play a role, or doesn't show up. So.
Is that maybe reflected by the fact that you have this way of collapsing from PPPA to PA?
Yeah, exactly.
Okay.
Yeah.
Question. Maybe that's stupid. Is this mapping supposed to preserve parallel compositions? So like is the P of AB PA/PB, or
There's different ways of preserving parallel compositions. And in the simplest case, no. You would have to specify what you mean by preserving parallel compositions, because, I mean, even in the naive case, I don't know if it makes sense to write here. Yeah, maybe. Hey, this is not a projector; it's a screen. Okay. What did I want to say? Like if I look at just P of A times A even, well, this is not going to be even like isomorphic to P of A times P of A, right? Actually,
I think that's the question.
well, it's not. It shouldn't be, right? Because these are going to be. Yeah, maybe we should think about that more carefully. So what is this thing on the left? These are the joint measures, right?
Yeah.
So these are going to be measures Q. I mean, maybe it's better to do different because then we can distinguish them. These are going to be joint states on AB. And what are these things on the right? These are going to be product states. Right? So you shouldn't expect them to be the same. It would actually be quite like pathological if they're the same.
I was thinking that you're mapping objects, not states. So if I map the object
No, but
P to object PA/PB, it does not mean that the distribution should be a product on PA/PB.
But the element, so if I think of this as the object in some concrete Markov category, then in many of the concrete Markov categories, the objects are some kind of structured sets, some kind of space. right? And so this is a space of joint measures, so it's this space, and this is a space of product measures.
Okay, I think I don't understand.
So
Because it's a tensor product, looks like you maybe are going to consider product measures, but also like convex, also like linear combinations of product measures, right? But that's not what this monodal project.
yeah, there's one point. I think what we were talking about is maybe a bit different. I'm not sure, but I think I was saying that for example, in Borel-Stokes, okay, let's just consider a concrete Markov category Borel-Stokes. Then this is a measurable space. What are the elements of the measurable space? Like Q is an element of this measurable space if and only if is a joint measure on A and B, okay? On the other hand, like P is an element of this measurable space if and only P is equal to this. So that's what I was saying, is that as sets or like spaces, these are quite different as spaces in Borel-Stokes. Like if I construct, so in Borel-Stokes I said there are distribution objects. So for any measurable space in Borel-Stokes, I can construct the corresponding distribution object. And if I consider in particular the A tensor B and then construct the distribution object, I get
I see.
the elements are these, and if I do this, the elements are these.
Okay.
And so I shouldn't expect them to be the same. However, there should be some way of going from one to the other. It's just not going to be an isomorphism, right? Like I can take a joint state and construct the marginals, and I can take, I mean, this is actually just included in here. So there is some kind of inclusion here and some kind of projection here, but they don't compose to identity.
Yeah.
Right? And so this additional structure is relevant, and now, yeah. So this you can require to exist additionally. Yeah.
Okay.
I have to recall. No, so like just the basic inclusion should also be in the definition. There's some more like additional properties you can require. Like that's the thing with category theory. Like it's not clear to say like P should be compatible with products. There are different ways of being compatible with products,
Yeah.
and that also gives you, as far as I know at the moment, at least 3 different notions of distribution objects.
Mm-hmm.
And what I kind of showed you is kind of this kind of basic one, but then you can like make it stronger with additional properties.
I see.
Yeah.
Thank you.
But I think this was a good question to kind of clarify this, because it's not obvious somehow. But I think we can maybe do another last question, but yeah, we're close, finishing off.
Is there any notion of functors between Markov categories that preserve the structure, and
Yeah.
are those kind of worth studying, like maybe a
Yes.
category of Markov categories?
Definitely worth studying. Has not been explored so much, but in some sense, rather than studying this like abstract nonsense of like, we rather look at concrete applications, and there it kind of shows up, because when you want to describe, for example, limits in Markov categories, well, what is a good notion of a limit in Markov category depends on what you think is a good category of Markov categories, and so that's kind of like an indirect way of studying that. Yeah.
Okay.
And so usually, so this we will get to tomorrow, because I didn't go into the Kolmogorov products, but Kolmogorov product is an axiom that is expressed in terms of a categorical limit, but it's not just a limit in the category, but it has additional properties, and these additional properties are about preserving the structure, which you could see as coming from the fact that functors between Markov categories have to preserve that structure.
Okay.
Yeah.
Cool.
But this is somehow, like, it's a very good question, but yeah, I would say it has not been spelled out in any paper very clearly. Like it's more kind of distributed in the literature at the moment. Yeah. Yeah. Let's close it at that. It's been 1.5 hours. Thank you.
Thank you.
Thanks so much.